Good evening and welcome to the live session. It is 6 p.m., but we have only one participant with us, so we'll wait for some more time to allow others to join. Thank you. Good evening, and welcome to week 7 of the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajin Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Over the past 6 weeks, we have been studying about additive manufacturing. We started with terminology and classification of processes, what qualifies a manufacturing processes as an additive type process. Um, we looked at the categorization of all additive processes, first based on the ASTM classification, and second based on the classification on the type of feedstock, which is something we are following for the purpose of this course. We have already looked at additive processes which use liquid feedstock, such as VAT photopolymerization, 3D systems SLA, 3D systems FL, and others. Last week we also looked at additive processes which use sheet as the raw feedstock, and we saw various additive manufacturing processes, some of them commercialized, which used sheets of any material starting from paper to ceramics and even metal, of course, as the raw feedstock. Another thing which we noted was that all sheet-based additive manufacturing processes are inherently of a hybrid type because if you just keep on stacking sheets of paper, what you will end up with is a cuboidal volume, and to extract the desired uh, part or geometry out of it, it must be machined in each layer. And thus, inherently, all sheet-based additive manufacturing processes are of the hybrid type. This week we'll be looking at wire additive manufacturing, which is also an area in which I myself am working. And among the wire additive manufacturing processes, we'll be looking at the classification of such processes, and we'll be going into some depth of the fused deposition modeling or fused filament fabrication, which is basically the 3D printer, which is most commonly encountered in these days, even in school laboratories or in UG labs, maker spaces, and other such similar places. It's the benchtop printer, which with you can make polymeric parts. And it will be looking at the feeding mechanism, the pinch roller mechanism, what are the power and liquefier dynamics, and also at the phenomena of die swelling, bead cooling, bead ironing, and surface roughness. The materials which can typically be processed using a wire-based AM technique range anywhere from polymer or composite to wax and metals. Um, these materials will, as the name suggests, be typically available in the form of a wire or a filament, and the filament will be fed through some deposition head onto the substrate. Now, the transfer of this wire from the 3D printing machine to the substrate or the pre-deposited layers can either occur in a continuous fashion or it can occur in a drop on demand fashion, where, say, somewhat similar to how for liquid based AM processes we had those deposition heads with hundreds or sometimes thousands of micro nozzles which would dispense the tiny droplets of the build material selectively or the binder material selectively in the over regions of interest. Similarly, in these processes also, we can have a drop on demand like mechanism where we are simply dropping the material dropwise into the regions where they're needed. The machine kinematics can be serial where say all the links are linked to each other sequentially and the end effector is linked to only one such link, or parallel where the end effector is linked to multiple links, all of which can move independently. Or typically it can be a hybrid kinematics, which has elements of both serial and parallel type kinematics. The energy sources which are typically used are something as simple as a resistance heating, which can give you temperatures of say up to anywhere between 200 to say 250 degrees Celsius or slightly more, but in this order. Or you can have induction heating, which may be used to melt metallic alloys, or you can have arc or energy beams, such as typically a laser or electron beam. And with laser beam and electron beam, the temperatures achieved in process can easily cross 3000 Kelvin. The support mechanisms uh, may be water dissolvable in the case of polymeric 3D printing using FDM or FFF. Um, Typically, as we have been discussing over the past 6 weeks, we want to have some distinction between our build material and support material. If our 3D printer has the functionality of multi-material printing, we can simply use two different materials, say one of which can be susceptible to chemical attack, or there may be some other way by which one can selectively be removed while the other one stays. However, we saw that when such a multi-material functionality cannot be availed or is absent, what we can instead do is make the support structure weaker, either say in the case of UV based processes where we printed both the build material and support material but did not fully cure them, then broke off the support materials manually and then put the part for the final curing process. Uh, or we can have some design strategy whereby we deliberately make the support structures weaker or less dense so that they are easier to break off. However, for FDM, typically the support mechanisms are water dissolvable, or we may have combinations where the support structures are selectively soluble in some acid bath. An example which we'll also encounter is that of stainless steels and copper, where copper is the uh, support material, and copper is it can be dissolved in nitric acid or HNO3. And of course, with latest techniques and the use of multi-axis multi-degree of freedom tables, we can just have multi-axis kinematics, which totally eliminate the need for support. The parts can be tilted such that they're always normal to the deposition surface or deposition head. Now, for deposition modeling or fused filament fabrication, the materials which are deposited are typically polymeric or some composite. The material flow is continuous. Machine kinematics is serial. The energy source is just your simple resistance heating, and the support mechanisms are typically water dissolvable. And in the mold of all other additive processes we have seen, even an FDM process will consist of three, say, blocks of processes, those being pre-processing, building, and post-processing. Just like usual, we'll start with the creation of a CAD model, convert that to an STL file. If you want to work with, say, an indirect slicing approach, uh, check uh, the orientation of the STL file to minimize the number of supports and check which are the facets which require support based on the orientation of the surface normals. Then all such supports will be generated. The 3D CAD model will be sliced and then the area filling toolpath will be worked out. Based on this, the G codes are generated and fed into this machine. So these first two rows of operations pertain to pre-processing. We are still sitting at our computer. We have not even been to the machine yet. We are uh, doing the pre-processing steps. The next two steps are the deposition of buffer layers and the deposition of the main and support material. This is the build step. Now, why would we have the need to deposit these buffer layers. If you remember from last week's discussion, even in processes such as Kira's paper lamination technique, we saw how before starting the actual print, a few sheets of paper were pasted using some adhesive glue onto the build plate. And this is to ensure good adherence of the material to be deposited with the base plate. It is very important because if proper contact is not established between the very first layer to be deposited and the substrate, we know that later either the build plate or the head will move, there will be relative motion, and that bottom layer, if it is not well bonded, can be dislodged or some cracks can develop, and overall, the build will be compromised. So these buffer layers are deposited to ensure adherence or good adhesion of initial layers with the build plate. A second purpose which they can serve is to provide the necessary machining allowance. Whereas rather than printing directly onto the build plate, we are printing on these buffer layers, which even if they get damaged, it does not matter because they are of a sacrificial nature. And once the main and support materials have been deposited, we will remove the support structures. In a typical FDM machine, this can be done using something called waterworks, where water is used to selectively dissolve only the support structures and then finish the surface to the required quality. So this last row pertains to post-processing. Now, FDM is one of the most commonly encountered, well-studied and commercialized 3D printing technology. And I believe almost all of us would have encountered it during our daily walks of life. Uh, some of the key mechanisms of the FDM process are highlighted in this one single picture. The top red box actually highlights the feeding mechanism. The blue box just below it highlights the heating mechanism where this uh, filament which was initially solid is liquefied. And then the bottom red box actually highlights the printing process or the deposition process where the liquefied filament material is then transferred onto the build stage and molded into the required geometry. The typical feedstock for an FDM process are amorphous thermoplastic polymer filaments with diameters ranging between 1.5 to 3 mm. If it's just a simple benchtop system, the feedstock may simply be available in the form of a loose coil or in the form of wire spool, whereas if it is a complex feedstock, we can see here this pair of rollers, which typically will be say connected by some spring to have tension. This is called the pinch roller mechanism. A stepper motor is connected to one of the rollers, providing energy to move the filament through the system. Typical roller materials are hypalon or polyurethane if your filament material is thermoplastic. However, if your wires are metallic, then the typical roller materials will be different. There will be some, say, metallic alloy like some non-corrosive grades of steel, which may additionally require some surface hardening to have longevity. Here we see that the build material is being fed from some roller or some wire spool. The spool also imparts some tension to this wire so that it does not uncoil all at once and is fed only at say the required rate. And typically at the start of print or the machine will be calibrated while being commissioned. But say even then periodically what we would want to do is calibrate these rollers, which is to check whether they are supplying or feeding the wire in the desired rate. So what we can do is there will typically be some specified tension or torque range for these rollers. We'll only tighten them within that specified or recommended range, and then feed some known value, say some 5 centimeter of wire through these rollers, and then initially we would cut the wire very near to the nozzle, and then check how much of the wire is getting extruded. And if this value is say very close to the desired value, we know that the calibration is fine and we can trust the feed rate from the rollers. But if it is off by a large margin, we'll need to calibrate again. Now, one or both of the rollers may have a grooved or a toothed surface. And the reason for this is because your wire will typically pass through this groove that we see near the center. So we can imagine our wire passing through here. And the reason for this is to maximize the surface area and to create sufficient friction for the roller to grab the filament and feed it to the liquefier without slippage. Of course, what we also know is if, say, there is a multi-material functionality, not only would the wire have to be fed in the forward direction, it would always also need to be retracted from time to time so that the other wire material can be fed. So it is very important to ensure that there is no slippage at all between the rollers and the wire filament. This is ensured by having a grooved or toothed surface where the contact area between the filament and the gears or the two rollers can be maximized and sufficient friction can be ensured. Because of the spring present here, as we can see, there will be some pressure buildup on the filament, and the pressure on the filament between the rollers is typically sufficient to just slightly deform the filament, uh, usually leaving some small tooth marks. But these should be designed so as to avoid crushing the filament because crushing will have undesirable effects where say it will not be fed to the material at the required rate. And an example of crushing is also shown here in the inset where maybe the rollers would have been tightened too much and the filament diameter has been worn down due to excessive friction from the knurled capsule and the filament egress path is clogged because now instead of getting fed say along a straight line, what we can see is now it is actually being fed at an angle. Excuse me. This can actually interfere with the feeding dynamics. We have a free body diagram of a section of the filament which is being fed through the rollers, through the rollers into the liquefying region. The pinch roller mechanism is used to supply material to the liquefier in FDM-like processes, and typically the filament feedstock will be in tension above these rollers because, as we said, it is connected to some spool of wire which is not free, but rather it will rotate at some specified rate to feed the wire. And so above the rollers, the filament wire is in tension which pulls the filament from its source. Below the rollers, the filament will be in compression. The reason being that the opening of the print nozzle is constricted, and that is, it has a smaller diameter than the nominal diameter of the wire. That is why some extent of deformation or crushing from the rollers is in fact desirable. Second, inside the liquefier, the filament material would already have been liquefied and will be available in a liquid state. And typically, there is a volume expansion associated with melting. So, the material inside is already expanded, and then we are feeding more amount of wire into it. So, it will be compressed. Therefore, for a given layer thickness T, bead width W, and transverse speed Vt, the volume flow rate required for complete filling is simply given by the continuity equation, which is flow rate is equal to cross section times the velocity. In this case, the velocity is given by Vt, and the cross section is nothing but the width of the bead into the layer thickness Wt. For a filament of constant diameter, the filament feed rate Vf depends on the flow rate and is given as Vf equals some correction factor Kf times 4q by pi df square. Kf is a correction factor to account for the friction between the rollers and the filament. Ideal gripping and feeding requires Kf to be equal to 1, but that will rarely be the case. If Kf is very large, very much greater than 1, then the filament is crushed by the rollers, and if Kf is less than 1, then the filament will slip. So typically we'll want a value of Kf which is just slightly greater than 1, but not very large. Again, if the pinch rollers are rotating at some constant angular velocity given by omega r, it can be related with Vf, which is the filament feed rate, as Vf equals omega r dr by 2. And this allows us to obtain an expression for the angular velocity of the rollers, omega r, in terms of this friction factor, the transverse velocity of deposition, the width of the bead, the thickness of the layer, the diameter of the roller, and the filament diameter of the filament. And this, given all the other say quantities, we can determine any one of them. Similar calculations are also available for power, and we see that the force necessary to push the melt through the liquefier can be determined in terms of the pressure drop. If the pressure drop is delta P, then F2, which is the force required to push the melt through the liquefier and outside, is delta P into pi df square by 4. If we have one driving motor, which is typically the case, the other roller is typically an idler, then the motor torque is F2 times the lever arm, which is dr by 2, or pi by 8 delta P dr df square. Then the motor power can be found as angular velocity times this torque, which is kf delta P Vt into omega t, which is nothing but the volumetric flow rate Q. Now, we mentioned that the filament below the rollers is in a state of compression, and because it is a filament-like material, it can also buckle, similar to the buckling phenomenon which we studied for columns. The compression of the liquefier's head of the feed roller places a limit on the volumetric flow rate Q. When this compression reaches a critical limit, the feedstock filament can buckle, as shown in some of the examples at the bottom here. Like here we can see that the material has buckled, and also on the right where the buckling is very extensive. and it is among the most common failure mechanisms on FDM machines. Now, if there is the phenomenon of buckling, we should also be able to calculate the critical load required for such buckling to take place. And this is all thanks to Euler beam theory. Now, in order to calculate the critical force, one may consider it as a buckling of columns. And it has been found that the case of feeding of filament through the rulers into the liquefying region is similar to the case of both ends pinned and a buckling load being applied, in which case the effective length turns out to be the length of the filament between the rulers and the liquefying section, and the critical buckling load turns out to be pi square EI by L square. Thus, the critical buckling load may be found as pi square EDF square by 16 LF square times this factor of 1.1 or an additional 10%, which is the correction factor due to difference in cross sections of the liquefier and the wire. Because remember, we said that the opening of the liquefier is constricted. Now, the liquefier or printhead is part of the machine where the solid polymer feedstock is melted and pushed through a small print nozzle. The dynamics of liquefier is quite complex and challenging to model, and this mostly arises from the fact that the melt properties are a non-linear function of temperature and shear rate. Because these materials are polymeric, they are non-Newtonian, and so typically they exhibit non-linear behavior, especially uh, the melt properties such as viscosity or thermal conductivity or specific heat capacity even will be non-linear functions of temperature as well as the shear rate. And a simplified derivation of a few of these quantities has been done by dividing the liquefying section into three zones, those being a constant or prismatic section of diameter d1, then a converging section, and then a prismatic section of a smaller diameter d2. Now, the force required to extrude the melt must be sufficient to overcome the pressure drop across the system, which strictly depends on the viscous properties of the same melt as well as on the geometry of the liquefier and nozzle. Because of the fact that melts adhere to the liquefier and diverge, the material is subjected to shear deformation given by the rate of shear deformation gamma dot equals minus dVdr. Thermoplastic materials, which are the typical feedstock of FDM, exhibit shear thinning. That is, the viscosity will decrease with increasing shear rate. So the more you shear it, the easier it becomes to shear the material. And this behavior can be fitted very well by using power law. And it has been assumed that adopting the power law for generalized Newtonian fluids for modeling of polymers such as ABS is sufficiently accurate for modeling of FDM melts. In the present case, the power law is defined as the shear force tau is equal to the shear rate gamma dot by phi power 1 by n, where tau is the shear stress, gamma dot is the shear rate, phi is the fluidity, which is nothing but the inverse of the viscosity, and m is the flow exponent. The general flow characteristics of a material and its deviation from Newtonian behavior are reflected by the flow exponent m. If m is larger than 1, then the material is pseudoplastic. If it is equal to 1, the material is Newtonian. And if it is less than 1, the material exhibits dilutant-like behavior. And this power law has been applied to the momentum flux balance of a fluid element across the zones 1, 2, and 3. And this allows us to find the total pressure drop. Another important assumption here is that the fluid is assumed to be isothermal at a temperature T which is equal to the temperature of deposition. However, this can lead to a few challenges which are listed here. The fluid was assumed to be isothermal at temperature T equal to the temperature of deposition. However, when a sudden change in the flow rate is applied at the entrance of the liquefier, the steady state condition of the flow is disturbed. But what can lead to such perturbations in the flow rate? It can be because of, say, uneven tension in the filament coil, or say, uneven winding of the coil, or it can be due to some lag of control, or it can be because of, say, uneven friction in the rollers, or any such region, or the wire surface may be, say, damaged or constricted in some region, which allows it to pass, say, much more easily than intended through the rollers. Any and all of these may lead to a sudden change in the flow rate, which will in turn disturb the steady state condition of the flow. With the introduction of new material in the system, the average velocity of the fluid increases and the average temperature drops. And in order to stabilize the new steady state conditions, the heat flow rate must be increased. Because now what is happening is that we have a larger volume of material coming in, but the amount of heat that we are supplying to this new volume is still the same. So its effect will be a lower rise in temperature than intended. If we want to maintain the isothermal conditions that we started with, and we have a larger quantity of material coming in, what we must do is also supply a larger quantity of heat. Since the temperature control is based on a single input from a thermocouple reading, typically at the end of the liquefier, the response of the system is delayed. Typically, this delay is of the order of seconds. The temperature is regulated via heat input from those electrical coil heaters, which are used for resistance heating. And the system continuously adjusts the power supply to the coils according to the temperature difference between desired value and value detected by the thermocouple, or simply the error in temperature. The response time of the temperature controlling loop is of the order of seconds due to thermal inertia of the extrusion assembly. And during the time of thermal adjustment, the flow can be non-isothermal. Temperature dependence of viscosity comes into the picture, as well as the shear rate dependence, because as we know, these materials exhibit a shear thinning behavior. And in such a case, the necessary heat flow rate supplied through the wall of the liquefier can be determined as in the given formula. Uh, the viscosity expression, because we must take into account its temperature dependence, can be obtained as eta equals some h, which is a function of t, times eta naught, which is a function of shear rate gamma dot, where ht accounts for temperature dependence, and gamma naught as a function of uh, eta naught as a function of gamma dot is expression for viscosity at some reference temperature T alpha, at which the value of the power law exponent m and the fluidity phi were considered. At reference temperature, this coefficient Ht will equal 1, and for some material, the value of alpha is given to us as 19,800. And what this all of this allows us to find is the total pressure drop across the three zones. And the key takeaway message being that when a sudden change in the flow rate occurs, the average temperature T drops and the velocity V increases, thus resulting in considerable increase for the pressure drop of the system. Uh, an example numerical was also solved by the couple in class. Next, we look at some of the other considerations in FDM-like processes, which are dye swelling, bead deposition, spreading and bonding, and surface roughness. Now, in the nozzle, the polymeric material is under stress because, as we discussed, uh, for most solids, the melting process is accompanied by an increase in volume. However, the volume of the liquefying region itself is fixed, so the molten polymer will be under compressive stresses with part of the deformation energy being stored elastically. When the polymer material is no longer constrained by the walls of the liquefier, the stresses that were acting on the melt in the nozzle are relaxed and the elastically stored energy will be released. And this happens when this liquid polymeric material is expelled through the opening of the nozzle, leading to a radial expansion of the melt, which is referred to as die swelling. What is happening is that the orifice of the nozzle has some nominal diameter d2, and when we are pushing or ejecting this liquid polymeric material from it, what we expect is the ejected material will also have a diameter of d2. But this does not really happen because the molten material has some amount of elastic energy stored inside it when it is ejected. The constraint from all the surrounding walls is released, and so the elastic energy can no longer be contained. It must be released, which leads to swelling of the polymeric droplet to a diameter d3, which is typically greater than d2. Quantitative measures of the dye swelling have been performed, and it is defined as the ratio of the maximum diameter of the extruded material to the diameter of the die opening. And the swelling ratio S is equal to d3 by d2, where d3 is the maximum diameter of the extruded material and d2 is the nominal diameter of the die orifice. The value of the swelling ratio depends on the material properties and the geometry of the extrusion nozzle. Some of the typical reported values are between 1.05 to 1.3. And inelastic fillers, such as ceramic particles or carbon fibers, tend to reduce die swelling. The reason for this is because it was the release of elastic energy which was leading to this die swelling process. If the material itself is inelastic, it will be incapable of storing elastic energy, or the amount of elastic energy stored will be negligible. And so, when such a material will be released, there will be no associated release of elastic energy and thus no swelling. After leaving the liquefied nozzle in a melt extrusion AM process, a bead of polymer melt ultimately lands on the substrate or on a previously printed bead of polymer. And if flow through the print nozzle region 3 is modeled as a simple Hagen-Poiseuille flow, the volumetric flow rate can again be calculated as pi times d2 by 2 power 4 del p, where del p is the pressure drop, 8 eta L2. The cross-sectional area of the bead will be inversely proportional to the velocity of the print head given by AB equals Q by Vt, where Q is the flow rate. If the print head velocity is sufficiently large, that is, if we keep this QB constant and increase Vt, what we should expect is an associated decrease in the bead area. With the bead cross-section area decreasing, there will come a transition region where it will become unstable and then simply become discontinuous. As the speed is increased, the bead area is reduced, and above a certain speed, equivalent to a minimum cross-sectional area, the bead will simply tear, producing gaps in the final part. Because what will end up happening is, on our substrate, rather than printing a continuous bead, the bead will be deposited with breaks, or it will be a discontinuous bead. And this can typically happen if, as in the present case, your scanning speed is very high, which leads to keeping everything else constant, will produce a decrease in the cross-sectional area of the bead, and eventually at real it becomes discontinuous. A second reason can also be uh, very low feeding rate of the wire itself, whereas if we keep other parameters constant, a lower feeding rate will lead to regions of starved deposition, where you simply do not have sufficient material to melt and deposit, and you have this discontinuities. The maximum achievable area at the maximum head speed is analogous to the problem of an axisymmetric liquid bridge, which is stable up to a height limit on the order of the square of the tip height above the surface divided by pi. Thus, it is equal to h square by pi, where h is the distance of the nozzle from the surface given here. And here we have a schematic representation of this critical threshold. The head speed is given as 1.5 and 2. These are just normalized values. Uh, that is velocity over the critical velocity. If they are equal, then we can expect the cross-sectional area of the bead to be prismatic and almost equal to the cross-sectional area of flow at the uh, orifice of the nozzle. If the head speed is 0.5, or if the speed is only half the critical speed, we are feeding the material too slowly, and thus it will tend to bulge out, and then the cross section of the bead will have an area which is twice the uh, area at the deposition orifice. Whereas in the other case, if it is being fed at a faster rate and the speed is twice the critical speed, then we'll see a corresponding reduction in the area, and this reduction will be this new area will only be half of the area corresponding to the area at the orifice. We also have an expression for this critical velocity, and in the limiting case, it is equal to pi square d2 by 2 power 4 del v by 8 eta L2 s square. And while liquid properties are not explicitly involved in the stability limit presented in this above equation, the impact of exceeding the stability limit and the ability of the material to neck down from uh, a bead sectional area AB to the minimum possible cross sectional area AB minimum varies based on the Weber number and the Reynolds number of the liquid. Again, typically when we deposit these beads, they do not really have a very sharp shape, say a rectangular cross section, but typically the cross section will have an oblong shape with rounded corners, as shown here. So here the substrate is lying here, and say the printing direction will be either uh, out of the plane or into the plane. The spreading rate and the final shape are dependent on the viscosity of the melt, as well as the relative surface energies of the bead and the surface on which it is printed. The interaction of the tip of the print head with the bead may further influence the evolution of the shape of the printed bead, which is to say whether we have some standoff distance between the deposited bead, or whether this head is, say, very close to the top layer of the deposited bead, will have an effect on the shape of the printed bead. As the bead spreads, it also cools, and the viscosity will increase until a solid state is reached. The final width of the rod determines the resolution that can be achieved in the print process, because typically your minimum resolution is actually the width of this single deposited bead. You cannot print any features smaller than this unless you also incorporate, say, a machining step. And then the contact area between neighboring beads is also determined by this final width. Because what we'll do is typically we will deposit these beads with some step over. Say for a particular process parameter combination, you already worked out the step over distance and optimized it based on the spreading behavior of the bead at that step over distance and some particular set of process parameters. But for a different process parameter, the bead may spread more, or it may even shrink down. And in that case, you will have either, say, excess overlap than you planned, or a lack of fusion between successive tracks or intertrack porosity. The rounded oblong shape of the bead inevitably leads to small voids in the part, because even if we are ensuring that there is sufficient contact, say, because after spreading they form these bridge-like structures, there is still this small region between two successive tracks which is susceptible to voids. The strength of the bond between neighboring roads and ultimately the overall mechanical properties of the part will depend on the contact area between those beads and the size of the voids. Bead ironing is the phenomenon where when the print head nozzle is in contact with the deposited bead, as we saw in this second case here, sorry, it was found to be beneficial, resulting in a more stable flow and ensuring a flat road surface. In the first case, what we are seeing is that there is some gap between the top surface of the deposited bead and the nozzle itself. And this leads to this phenomenon of road distortion, shown on the right here, where you have some bulging and unevenness in the height of the bead. Whereas in the second case, mm, the gap between the nozzle and the top layer of the deposited bead is zero. They are in contact, and this has the additional impact of ensuring a flat surface. In this case, another difference which we can clearly see is that there is a significant amount of deposition ahead of the deposition head, which we also see in processes like laser-based uh, 3D printing, such as in SLM or DED, where you will also have some, say, if this is the center position of a laser beam, you also have some material ahead of it and some material behind. Of course, this oblong shape is because of the travel or motion of the laser beam, but you always have some material ahead of it and some behind. Similar is the case for the bead ironing phenomenon, and the distortion of the road uh, when the printhead was above the root surface can be speculated to be due to effect similar as seen in dice. The strength of melt extrusion will be limited fundamentally by the strength of the bond between neighboring beads, as you just saw. And this bond strength in turn will be a function of the energy of adhesion if the two beads are of dissimilar materials, or cohesion if the two beads are of the same material, which will depend in part on the contact area between the beads. For polymeric materials, the bead bonding occurs through a sintering process which emerges through a viscous flow mechanism. And as the sintering process is thermally driven, the temperature history of a rod at the interface with another rod becomes a crucial variable in determining the quality of the bond. And on the right here, we have this nice schematic diagram which explains the various stages of sintering and say contact generation between two adjacent beads. Initially, there is a contact between the rods, very small contact between these two rods. Then there is neck formation where the contact length 2y is smaller than the diameter of either grain, which is 2a. Then there is an interdiffusion of polymeric chains and growth of the neck. And then finally, there is randomization of polymer chains between the adjacent rods. The neck length 2y gives an measure of the bond quality, and if it is equal to 2a, then what we can see is that this surface will become flat. Now, typically, the oblong shape of the deposited bead is assumed to be uh, an elliptical cross section, and the filament cross section area and perimeter can then be determined as given here. The area will be equal to pi times AB, and the perimeter will be equal to pi times A plus B times 64 minus 3 lambda 4 by 64 minus 16 lambda square, where lambda is equal to A minus B by A plus B, where A and B are the semi-major and semi-minor axes of the elliptical cross-section, respectively. Typically, we just assume a uniform temperature distribution throughout the cross-section, that is, across this entire cross-section. The temperature is the same, and there is no distribution or variations in temperature, which then essentially reduces this problem to a 1D heat transfer problem, where the temperature variation is only along the scanning direction, which in this case happens to be the x direction. The cooling process of a single filament is thus simplified into a one-dimensional transient heat transfer model. A single deposition rod is modeled as a one-dimensional block. The heat moves at a constant speed of v along the x-axis. Sorry, the head moves at a constant speed of v along the x-axis when extruding. The origin of the reference coordinate is set at the extrusion head, and this becomes a problem of a moving reference frame, which is something you might have encountered in our analysis of welding, where say the Rosenthal solution uh, has uses a similar technique where the reference frame is actually fixed to the moving energy source. It is the mass of the foundation, that is the build plate, is much higher than that of a single filament track. The conduction at the interface will not appreciably change the temperature of the foundation. Thus, the heat loss by conduction from the filament to this foundation can actually be approximated as just a convective loss to the ambient temperature at some with some heat transfer coefficient. Because if it is considered as conduction, then we also have to account for temperature changes into the foundation. It will not be maintained at a fixed temperature. But what we know from our knowledge of FDM processes is that typically the build plate will not be at ambient temperature. We'll be preheating it to say 60 or 70 degrees Celsius, and we'll be maintaining that temperature with some heating and closed loop feedback mechanism. Thus, it is far, far easier to actually model the loss of heat from the filament to the foundation in the form of convective losses only. The governing equation for this system then becomes rho Ca dou temperature dou time equals A dou x K dou T dou x minus the heat lost due to convection Hp T minus T infinity. And the boundary conditions are also given to us at T equals to T naught, at x equal to 0, the T is equal to T naught for all times greater than equal to 0. And at very far away x, the temperature T equals the ambient temperature for all times greater than T equal to 0. The term H covers the effect of both heat convection with air and conduction with the foundation. The origin is moving with velocity v, where x is equal to v times t. And the time dependence term dou t can be transformed as dou t dou x times v, assuming that the velocity is constant. The governing equation is then reduced to an ordinary differential equation of the form rho c a v dou t dou x equals a dou x k dou t dou x minus hp t minus t ambient. And this equation has this closed form analytical solution given by t equals t infinity plus t naught minus t infinity times e power minus mx, where this parameter m is given as under root of 1 plus 4 alpha beta minus 1 by 2 alpha, and alpha equals k by rho cv, and beta is equal to hv by rho c av. The cross-sectional area of the bead will again be inversely proportional to the velocity of the printed, as we already saw. This velocity is not constant at the beginning and at the end of the process because we are starting from rest, uh, then we are accelerating to some voltage, which is a finite process. It will not happen instantaneously, it takes some time. And then we are stopping. Again, we cannot just stop instantaneously. Uh, the deposition head will come from a non-zero to a zero velocity over some time. The velocity varies at the start and stop of each successive layer, as well as when there are sharp turns, because of the acceleration associated with turning. Either there will be variations in velocity, that is, at a corner we want to reduce our velocity and then accelerate again, or even if we maintain a constant speed, because of the change in direction, there is still an acceleration associated with it. Most sophisticated systems simultaneously adjust the filament feed rate to compensate for this. However, any degree of lag in the feed rate controller will result in a corresponding degree of under or over deposition as the printhead accelerates or decelerates respectively. And this is also illustrated here in the graph at the bottom, where we have the red curve showing the variation in the velocity and the yellow curve showing the variation in the uh, material deposition rate or flow rate. Initially, the velocity is essentially zero, and even then, since our material has is getting melted and released from the orifice, there is some deposition. Then the velocity increases. Because of this, in the first region, we have this over deposition. Then the deposition rate becomes constant, but the velocity is increasing, which leads to an uneven uh, cross section of deposition. Then the velocity is also constant, and the material flow rate is also constant, leading to steady state deposition, typically in the middle of the bead. For processes like selective laser melting, such steady state is achieved within, say, 3 millimeter of the originating point of the bead. Then, once we have to stop, the feeding rate remains the same, or the flow rate remains the same. However, the velocity decreases, which leads to over deposition again. And finally, the machine head comes to a full stop, and the flow rate is slowly brought down to zero. One can adjust the flow rate with VT by changing the filament speed appropriately. However, with latest innovations in FDM technology, uh, adaptive adaptive nozzles with variable cross sections have been developed, where the cross section of the deposition nozzle can be varied in real time, say while turning a corner or at the start or stop of the process, to ensure consistency, bead width. Another advantage of such adaptive nozzles is that they may also be used uh, for both filling the perimeter as well as the area filling. Because previously we have discussed how we need for the perimeter pass, the deposition has to be very precise. And so typically this is performed either at a slower scanning speed or if possible with say a laser or energy beam of a smaller diameter to have more control over the process. Whereas the area filling can be done at with a coarser beam spot size, or at a higher speed. However, if we are using an adaptive nozzle, what we can do is use the same nozzle for both the perimeter and the infill passes. At the perimeter, we just constrict the cross section, whereas for the infill, we increase the cross section. And due to the principles of AM, many accuracies are inherent in AM. One such being the resolution and the staircasing effect associated with STL files. Other sources of inaccuracy are warpage and shrinkage of the deposited parts, which we have discussed. And warpage typically occurs due to thermal gradient in the build part. Another defining feature of parts made with extrusion AM processes are the edges along the surface that result from individual elliptical beads in deposited adjacently to one another, which is called the stair-stepping effect. And improving this surface roughness by adjusting the design parameters often comes at cost of significantly increased build time, which cannot always be afforded and is not feasible all the time. As a consequence, post-processing via mechanical abrasion, machining, or solvent vapor spooning is pretty common for parts produced with extrusion AM processes. And the final section is on surface roughness of fused deposition modeling. Although frequently discussed qualitatively, surface roughness can quantitatively be defined as either arithmetic average values or as RMS values, RMS being root mean square. The average surface roughness, RA, is the mean variation in distance of a surface profile to the measurement center line, thus being the center line average CLA, which is equal to 1 by L integration from 0 to L, the absolute distance of x dx, where L is the sampling length or the evaluation length, Fx is the distance of the measurement point on the surface profile from the measurement center line. But what is the center line and how is it defined? Once a profile has been given to us, it is our job to first fit a center line, which is basically a line which has equal areas above and below it. So the line which I have just drawn may not be a very good center line, but this may be. The center line has equal areas below and above it. However, as we'll see, the centerline average is not a very reliable quantifier of surface roughness because surface profiles with very different characteristics can have the same centerline average. The RMS surface roughness is far more reliable and better accounts for isolated surface defects. It is defined as RQ equals square root of 1 by L is integral 0 to L fx squared dx. The surface roughness and influence of design parameters were also discussed by Professor Kapil in class. So I'll not repeat this again. Let us quickly go to metal wiring. And Professor Kapil started with the history of the process and some of the earlier efforts. Some of the first processes which did not have the same name but had the same idea, and then when moved on to shape deposition manufacturing and its steps. For metal wire additive manufacturing, the material or the wire filament is made of metal. The deposition process is again continuous. The machine kinematics are typically serial or parallel, as well as it can be hybrid as well. Energy source is typically in the form of arc or beam, and the support mechanisms typically are not used. That is, we use multi-axis kinematics, or if they are used, as in the case of stainless steel and copper, they may be selectively dissolved using an acid bath. The processes which use an arc energy source include wire arc AM or WAM, MIG, TIG, and plasma-based deposition. And the processes which use an energy beam as energy source are wire beam additive manufacturing using either a laser beam or an electron beam. Shape deposition manufacturing is one type of wire-based additive manufacturing which does not use our conventional slicing but rather uses segmenting. Like FDM, this also uses two heads, one for the model and one for the support. Shape deposition modeling is based on the premise that the invisible surface of the model will be the visible surface of the support and vice versa. If the model is visible, the model is made, and if it is invisible, the support is made. This way, the model and the support materials are created alternately. The creation of model or support involves deposition and machining, so it is inherently a hybrid process. The slicing, as we discussed, is not typical slicing but rather segmenting, and it makes use of visibility concepts. The part is therefore free from staircase effect, also because it is frequently machined, and the finish will match with the intended geometry. The deposition creates near net shape and quickly, and a 5-axis CNC machining is used for net shaping. It also makes use of short peening to relieve the stress. We know that short peening is a technique which is used either for stress relieving or in some cases also to introduce compressive residual stresses into a part. Uh, Parts manufactured via a fusion process which will undergo a phase change, that its solid material will be melted and then solidified again. Typically will have some compressive stresses. Tensile compressive stresses can be deteriorating and dangerous because we know that no microstructure is perfect. Part will have some internal cracks, and tensile residual stresses will only serve to enhance the crack propagation and growth of cracks. Whereas compressive residual stresses will help to close these cracks. This short pinning is a very useful strategy, and a variety of deposition methods are used. A variety of materials have been attempted. Our focus though will be on the metallic materials. And some of the various deposition methods which have been used in shape deposition manufacturing are extrusion, two-part resin systems, hot wax dispenser, photocurable dispenser, microcasting, welding, thermal spraying, and laser welding. The last four being microcasting, welding, thermal spraying, and laser welding are all some variation of the welding process. In microcasting, we deposit discrete superheated molten droplets to form dense metallurgically bonded structures. Materials for microcasting include stainless steel and copper. The reason for using superheated or for heating these metallic materials to a superheat and not just the melting temperature is because when this molten material droplet is falling or comes in contact with the pre-deposited layer or the substrate, it is not sufficient that the material itself was molten and then solidified. You also needed to uh, melt some volume of the pre-deposited layer or substrate in order to have dilution. In the absence of proper dilution, which is typically between say 10 to 30%, the metallurgical bonding between the deposited material and the pre-deposited layers or the substrate material will be very weak, and the part will have poor mechanical properties. Copper can be used as a support material, and it can be further removed by etching with nitric acid. For microcasting, an arc is established between a tungsten electrode and a feedstock wire, which is fed from a charged contact tip. The wire melts in this arc, forming a metal droplet at the end of the wire. When the droplet has grown sufficiently, its weight will overcome the surface tension and it will fall to the pre-deposited layer. While falling, the droplet is further accelerated by gravity and it flattens upon impact. The magnetic field also helps in the acceleration. Due to a large volume to surface ratio, the droplet will remain superheated in flight and will contain sufficient energy to locally remelt the underlying substrate to form metallurgical bonding. And to control oxidation during this process, the droplets and working area are locally shrouded with a laminar curtain of shielding gas such as argon. Uh, for this purpose, a commercially available shrouding device is used. And typically, the application of microcasting has been to deposit stainless steel and copper. And here we see how the TIG welding process is used for fine deposition of the exterior, whereas the MIG deposition process is used for interior deposition of infill at a high deposition rate. And for an arbitrary geometry and a part which requires support structures, we have the segments and the steps for a shape deposition modeling process. We see how, as opposed to say layers, uniform layers, we have these segments or non-uniform slices of material, and in each slice, the deposition sequence can be altered, as in it's not necessary that we always first deposit support and then deposit the material, as we will see in some cases. The build material may be deposited first, and it may be used to support the support material, which will be deposited subsequently. In conventional processes, the modeling material and support material will be deposited only once per layer. However, in shape deposition modeling, the model and support materials may be deposited alternately within the same layer so that at any time the region of deposition is free from undercuts. Each such deposition of modular support material is followed by 5-axis CNC milling, which is what is responsible for the very good finish and tolerance. The slicing strategy is independent of edge approximation. Slicing is done at strategically chosen Z values where transitions between undercut and non-undercut surfaces occurs or where there are changes in material composition for multi-layer printing. Here we see how for different layers the sequence of support and build materials can vary. Here the support material is in blue and the build material is in yellow. For the slice uh, B, what we can see is that The support material is deposited first, followed by depositing the build material in yellow. However, for the slice marked by A, the sub build material is deposited first, and only then the support materials can be deposited. And in the slice shown by C, we see that they can alternate within the same slice. As in, first we can have these two segments of support material being deposited, then some build material, then some support material again, and then further build material. The SDM process consists of several cycles of, say, either deposition of support and then machining of support, or deposition of model and then machining of the model. And any of this can be the first step. Another advantage of the SDM process is the ability to print multi-materials, as we see here, or the ability to embed some sensors or some micro devices and thus enhance or add multifunctionality to the printed part. And here, for a simple example, we see the adjacency graph, the minimal precedence graph, and the building tree expansion. So for the geometry given here on the right, imagine that we have to deposit it and how we can go about it. The first step is to identify all the unsupported faces, other overhanging features, such as this face of 2 is unsupported, then this face of 5, this face of 3 here, as well as this face of 6. Now that we have identified the unsupported faces, what we know is that before depositing those particular segments, we must deposit the other segments which will support them. Thus, the first segment which can be deposited for this is only 1, because without depositing segment 1, none of the other segments can be deposited. Once we have deposited 1, our other options are depositing 5, 2, or 6. But we see that 5 is still largely unsupported, 2 is also unsupported in the absence of 6, and 6 is the only one which can be built next. So the second precedence goes to 6. Once 6 is deposited, we can only deposit 2. However, once we have 2, we can either opt to deposit 5 or 7. 3 cannot be deposited because of this unsupported face of 3 here. So once 2 is deposited, we can either opt to deposit 7 or 5, which is also shown in this graph here. After depositing 5, we can have 3. 3 and 7 must be deposited independently of each other. However, both are required for the deposition of 4. And this can be expanded into this building tree, which shows us a sequence of steps depending on the choices we make. The adjacency graph or the adjacent graph shows us which segments are connected to which other segments. And this is also illustrated here, where we see that, I mean, irrespective of the flow that we choose, we will end up depositing the same path. So with that, we have completed a brief recapitulation of the contents for this week. Let us now break for a short while, and when we return back, we'll solve some example questions. Hello and welcome back to the live sessions. Let us now look at a few example problems which will help reinforce our concepts and will also prove useful for solving the assignment problems and for the course certification examination should you have registered for it. The first question is asking us in the FDM process, the maximum diameter of the extruded material is 1 mm and the diameter of the die opening, that is the frit nozzle, is 0.75 mm. Then find the swelling ratio. So I'll just draw a schematic here. We discussed that because of the elastic energy stored within a polymeric material while it is in the molten state, uh, when it is released from the nozzle tip or the orifice, there is a small expansion seen as this elastic energy gets released. The same is not the case for inelastic materials because the amount of energy stored in them is comparatively very small. However, for polymeric materials, we'll see a bulging leg effect, which is called die swelling. We are asked to find the swelling ratio, which is the ratio between this. It is the ratio between D2, which is the die opening or the diameter of the print nozzle, and the maximum diameter of the bead, which is D3. S is equal to D3 by D2. In this case, D3 is given to us as 1 mm and D2 as 0.75 mm, or this is equal to 4 by 3 or 1.33. 1.33 corresponds to option C here. So C is the correct answer. Let us also quickly revise the expected range of this die swelling, which we saw was in the range of, if I remember, 1.05 to 1.3 or similar. Yes, the typical range is between 1.05 to 1.3. The second question is asking us two filaments A and B of diameters 1 mm and 2 mm respectively of the same material and the same effective lens are to be printed using FDM process. Calculate the ratio of the critical force PA critical by PB critical between the pinch rollers and the liquefier to avoid buckling. Assume hinge condition at both ends. So this is the case corresponding to this, and I will just rewrite the same formula here. P critical equals 1.1, which is the correction factor, times pi square EDF square by 16 LF square. This is for one material. We can find this for both materials and take the ratio. However, a few key things to note. Here, 1.1, pi, and 16 are like numeric constants. It is given that the two filaments A and B are of the same material. So the Young's modulus E for both will also be the same, and they have the same effective lengths. So this parameter LF in both cases will also be the same. So what we say is the only quantity which will differ across the two cases will be df square. And so for finding this ratio of PA critical to PB critical, this will simply be the ratio of the diameter of A squared to the diameter of filament B squared. And what is given to us is that the diameter of filament A is 1 mm and that of filament B is 2 mm or 1 by 4, which is equal to 0.25. 0.25 corresponds to option A here, and so A is the correct option. Question 3 is asking us what advantage or advantages does parallel kinematics offer over serial kinematics in the context of FDM or fused deposition modeling? Let us recollect that serial kinematics is the case when the links are connected to each other sequentially and the end effector is connected to only one link. Whereas in the case of parallel kinematics, uh, several links may be connected to the end effector and each of these links may operate independently of the others. But what advantage does, say, a parallel kinematic mechanism offer over a serial kinematic mechanism? Does it offer greater accuracy? Does it offer greater build dimension in the z direction? Or does it offer a smaller footprint in the xy plane? Now we have discussed this point before also, and what we noticed is that typically parallel kinematics will have a smaller footprint in the xy plane. So your uh, say you need not have a very large uh, xy footprint, and it will only be slightly larger than your desirable build region. And typically they will also have, they can be very tall, and so what you'll end up having is a greater build dimension in the z direction. Your build volumes can be very tall. However, we do not have conclusive evidence to say that parallel kinematics will build parts that will necessarily be, say, more accurate or will have better tolerances than a part built by serial kinematics. So both B and C are correct, meaning that option D is the correct option. Question 4 is asking us, what drawbacks can you expect in a part built by drop-on-demand fused deposition modeling as compared to continuous fused deposition modeling? And let us just draw a quick sketch here. This was the continuous fused deposition modeling, whereas in the case of drop-on-demand, the deposition happened in the form of these discrete drops of material, and they were deposited in regions wherever needed instead of being deposited continuously. And what can we expect? What drawbacks can we expect in the latter? Are they more susceptible to lack of fusion pores? Will they result in a worse surface finish? Uh, are they more susceptible to interlayer delamination? So let us just draw a magnified image of the same, say where we just have a few of these particles. Now, since here the deposition is in the form of these discrete drops, what we can clearly see is all of these regions between these drops are indeed susceptible to the formation of voids, and so the lack of fusion pore formation is highly probable. Second, because these are deposited in the form of these discrete spheres or drops, you will always have these undulating features on the top surface. Whereas, say, compare that to a continuous deposition where at least the top surface with bead ironing can be made, say, sufficiently flat over sufficiently long distances. So it is expected to have worse surface finish. However, interlayer delamination would occur when fracture or delamination would occur um, across layers. However, that strength is guided by the fusion of these drops. And we have not really studied the dynamics, and we can't say for sure whether it is necessarily, susceptible to interlayer delamination as well. Because for all we know, these drops are also deposited in superheated state, and the fusion that they achieve with the drops of a previous layer may just be sufficient to prevent interlayer delamination. And so the correct option are both A and B, and the correct option is D. The fifth question is asking us, what is the exact perimeter of an ellipse with a semi-major axis of length 10 millimeter and a semi-minor axis of length 6 millimeter? This is 2A and 2B. A is given to us as 10 mm and B is given to us as 6 mm. And the formula for this was also given to us. Yes. The perimeter is equal to pi times A plus B times 64 minus 3 lambda power 4 by 64 minus 16 lambda square. Where the parameter lambda itself is equal to A minus B by A plus B. And thus, if we are not careful, what we'll do is just plug in the values of A and B into this formula and start solving for the perimeter. And whatever number we get, we'll write it. However, the thing to be careful about is that the formula given here is not an exact formula, it's an approximation. Because the perimeter of an ellipse does not really have a closed form solution. It is available in the form of a series solution, the accuracy of which will be dependent on the number of terms of the series which you are considering in your computation, but it will still never be exact. And so the exact perimeter is none of the above. The next question is asking us, what is the difference between shape deposition manufacturing and conventional additive manufacturing? Does SDM use segmentation, whereas AM uses slicing? Does SDM use subtractive operation in every step, whereas classical AM does not? In AM, can the support material support the build material, whereas in SDM, both and support materials can support each other, or is it all of the above? Let us examine these options one by one. We saw that in SDM, uh, the concept of segmentation is used, whereas in the same segment, we can deposit the material in multiple iterations or multiple layers. So option A is correct. Second, we saw that the SDM process has very good tolerances of the finished part, and that is achieved because of the 5-axis CNC machining, which is done in each step after the deposition of either the build material or the support material. So, in every step, SDM uses a subtractive operation, which is typically not used in the AM process, either though sheet lamination with or laminated object manufacturing, uh, which is a hybrid process, is also counted as additive manufacturing. Classical AM still does not. Again, we also saw that for an arbitrary geometry, it is very probable that in a same segment of material, the support can be deposited first and then the build can be deposited as the usual case. However, in a few cases, the build material can be deposited first, on top of which the support material has to be deposited. And so the build material can actually support the support material itself. And so all of the above are true, and option D is most appropriate. Question 7 is asking us, what is the purpose of preheating of the build platform in an FDM process? Is it to ensure a higher thermal gradient? Is it to ensure adhesion of part to the build plate? Is it to ensure cohesion of part to the build plate? Or is it to minimize the power consumption in the liquefier? Now, if we are preheating the build plate, the power used for this will of course be counted in the overall power consumed by the machine. However, it is not really linked to the power consumption of the liquefier because the resistive heating in that region is separate from the heating of the build plate. Cohesion of the part to the build plate uh, would have come into the picture if the deposited material would be the same as the material of the build plate. However, we know that typically in an FDM like process, the build plate will be metallic. It will be flexible but still made of some metallic alloys, whereas the deposited material will typically be some polymer or thermoplastic. So cohesion does not come into the picture. Is it to ensure adhesion of the part to the build plate? Yes, it is. And is it to ensure a higher thermal gradient? If we are preheating the build plate, typically in the absence of preheating, the temperature of the build plate would be same as ambient temperature, say around 24 degrees Celsius. But if we preheat it to 60 or 70 degrees Celsius, the temperature gradient, which say in one dimension would simply be dou t dou x. Assuming that the distance is the same, this dou t or delta t term will be smaller if we preheat the surface because now earlier say the deposit was at 250 degrees Celsius and the build plate was at 24 degrees Celsius. Now the deposit is still at 250 degrees Celsius, but the build plate is at 70 degrees Celsius. So we see that in this case, delta T has gone down, and so the thermal gradient has gone down instead of increasing. So option B is the correct option. Question 8 is asking us, which metric is preferable between centerline average RA, and the root mean square or RMS average RQ for reporting surface roughness of a 3D printed part. Is it RA because of ease of calculation? Is it RQ as it accounts for isolated surface features? Is it RQ as array of two surfaces for the same can be the same, but RQ will generally be different if the shape profiles are different? Or is it some combination of these options? We already know that RQ better accounts for isolated surface features because this is something Professor Kapil also discussed during the lectures. But what we also see is there can be surface profiles which are very different, such as a sinusoidal wave, a square wave, say a triangular wave, or a sawtooth profile. All of these can have the same centerline average surface roughness. However, generally the RMS surface roughness will be different. And so RQ is a better representation of the surface roughness. Hence, both options B and C are correct. And that was all that I had to discuss for today. Sorry for exceeding the time for this meeting. I thank you for tuning in to week 7 of the live sessions for the course on fundamentals of additive manufacturing technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you again next week. Thank you very much.